Yeah, we work together in Center for Geometry and Computational Design. We work together with architects and designers, and they are really interested in surfaces, either smooth or discrete, that are continuous flexible. And so, yeah, we found this very old paper by Sauer and Graf from the 30th century of the 30 years of the last century, where they introduced several classes of surfaces, smooth and discrete, that are continuous flexible, but they didn't give any explicit parametrizations for the discrete surfaces or especially for the deformations. And yeah, that is what we did. And we also, I would say, unified the discrete theory with the smooth one that were treated more parallel in the old paper. Yeah, among these different classes, there's one called T-surfaces, where we can see a picture on the left. They're called T-surfaces because in the discrete case, we have a quad surface whose quads are trapezoids. And yeah, I will now introduce how these are constructed and then how they can be deformed isometrically. And then in the second part of the talk, Arvin will explain us the situation for the smooth counterpart of these discrete surfaces. So the discrete surfaces are called T-hydron. So let's start with the construction of them, giving two orthogonal planes in the space, here Q0 and P0. In our talk, we will always assume that P0 is the XY plane and Q0 is the XZ plane. And in these orthogonal planes, we choose some polygons. The blue polygon here is called the profile curve, and it lies in the plane Q0. And the red polygon is called the prism curve, which lies in the plane P0. And we have some additional conditions, like that the prism curve has to have positive curvature, which in our case just means that the dihedral angle between consecutive edges lie on the same side of the curve. And then we can construct a third curve or choose a third curve, the trajectory curve, where we demand that the points of the trajectory curve lie on the extended edges of the prism. And if we have this initial data, we can rotate the plane Q0 around the prism curve, so that the first point of the profile curve traces the trajectory curve. And if we do so, we obtain the quad surface. And these quad surfaces are T-hydron. Now we want to obtain explicit parametrization for these surfaces. We have to consider the special equiform motion group, S2+, which is given by scalings that are denoted with mu, rotations, and translations. And the group operation is chosen in a way that we first scale and rotate and then translate. This is a subgroup of the normal affine. And now we want to define the action of this group on points in R3. And we do it by demanding that the Z direction is always preserved. And since we want to have a linear representation of the group, we embed R3 into the projective space just by choosing homogeneous coordinates. And then we can write down the transformation in this following matrix form, where in the upper corner we have the stretch rotation, and here on the right we have the translation. Just to go further with some more notation, if we just consider a translation, we will denote it with T. And if we have a stretch rotation around the Z-axis, it will be noted by R, and stretching factor mu, and the angle of rotation theta. And now, yeah, since we want to perform the rotation of the plane around the prism, we need to stretch rotate around other points than just the origin, and this can be obtained by the following concatenation of maps. First, we translate by minus P, then we stretch rotate, and then we translate again by P, which then gives us, yeah, the following form. And yeah, we have to do several transformations, and that is then called the discrete motion path. If we have a sequence of these maps that starts with identity, we will call this a discrete motion. Now we are ready to define the parametrization of the T-hedra by just applying the motion path to the profile curve. And the motion path is defined by the prism curve O and the trajectory curve delta. And yeah, the angle of rotation is always given by the dihedral angle of consecutive edges. And the stretching factor can be computed from the distance of the trajectory curve to the prism curve and the length of the prism curve, as you can see. And so we obtain a proper parametrization of the T-hedra. And the motion curve can now be written in the following way, where we see here that the stretching factor is given by the product of the moves, the rotation is given here, and this is the translation at the end. Before we come to the deformation of these surfaces, just let's consider some of the properties. The first and very important one is that the T-hedron is uniquely defined by the profile curve, the prism curve, and set of positive numbers that gives the distance from the prism curve to the trajectory. Further, all the perimeter lines of a T-hedra are planar, and the horizontal lines lie in the planes that are defined by the z value of the profile curve, and the vertical lines lie in the planes that we obtain after rotating the original plane Q0. Further, all the horizontal edges of a T-hedron are parallel for fixed E, which turns all the quads into trapezoids. That is where the name T-hedra comes from. Now, after we have seen the construction and the parametrization, we want to come to a classification of this T-hedra. They can either be classified by the motion curve or the planar curves and the positive numbers defining them. The construction that I've shown you is the construction of a T-hedra of the third kind, which is the most general case. The motion curve is obtained by translations, rotations, and stretchings, which we have the picture here on the left at the bottom. And there we can consider the special case if we don't have any stretching, but just a rotation around the fixed prism curve that we see here. These surfaces are called discrete molding surfaces. And they're special because the tetrahedrons are isosceles situations. So the vertical edges of a tetrahedron are always the same. And we have, as you can see here, it's the same stretching factor. The second kind of T-hedra are obtained if we shrink the prism curve to a single point and just apply a stretch rotation around this point that we can see here in the middle. And if we don't stretch but just rotate, we obtain the surface of revolution, a discrete one, where again the trapezoid is isosceles. The last and third kind is obtained when we think of the prism curve to be a point at infinity. Then we don't have any rotation, but just translations. And the surfaces that we obtain this way are translational surfaces whose quads are parallel. Now we can come to the isometric deformation of the T-hedra that preserves the class. And what is meant by that? That is, we consider a continuous map from some interval into the set of T-hedra of a fixed class. So if we start with sigma k in tk, we always obtain a tetrahedra of the same kind. And during this deformation process, we demand that the shape of all quads of the surface are always the same. And since the quads are trapezoids, they're uniquely defined if we know their edge length, where we have here the vertical edge length given by E and the horizontal edge length denoted by G. And for each quad, we just have to know one angle. Then the tetrahedron, then the trapezoid is uniquely defined. these information. Our strategy for the computation of the isometries is the following. At first, we will bend the profile curve isometrically. Since the profile curve is lying on the surface, we only can bend it isometrically. And this is obtained by scaling the x part of the profile curve and then compute the z part in such a way that the edge length is preserved, which can be done by this set of difference equations. And after we deformed the profile curve, we have to find the new prism curve and the new lambdas so that we then can construct the new surface. And to obtain these new quantities, we have to solve the following set of equations for a given pattern. All right. Let's have a look how it works in the first case, which is quite easy. These are the translational surfaces that isometric deformations are well known for a long time. And yeah, they're easy because one set of edges is determined by the profile curve and the other set of edges is only determined by the trajectory curve. So these are already separated equations that gives us that both of the curve have to be bended isometrically. And then from the third set of equations that it's given by the angles, we know how we have to transform the trajectory curve, how we have to bend it if we bend the profile curve, as I said before. It's quite similar. Here we have three pictures, how this involves. If the one curve gets less and less curvy, the other one gets more and more curvy. And we can also have a look at a video how these deformations are performed. So again, these curves get less and less curvy, and the other one gets more and more. Let's come to the next class. The second class, that is obtained by applying a stretch rotation to the profile curve. Geometrically, we can obtain the angle of rotation and the stretching factor by considering the polar coordinates of the trajectory curve. Then we obtain the stretching factor mu by this and the angle theta. And again, if we transform the profile curve, as I introduced at the beginning, we have to find now the new stretching factor mu and the new angle theta, such that the edges and angles of the surface are not changed. Don't really look at formulas in particular, they're just for people who want to read it later. But the only thing you could see that the first equation for E just involves gamma and mu, and the edge length of gamma, which is preserved, so that we can use that to solve the equation for the mu's and obtain them. Then we can look at the second equation and solve it for D, which are the scaled, there shouldn't be a D, there should be a G, I'm very sorry. If we did that, then this G is the scaled version of the edge length of the trajectory. And if we solve that for G, then we can plug everything in the last equation to obtain a difference equation for the angle theta. Yeah. So in this case, in the second case, these equations can easily be solved. And it becomes more and more complicated in the third case. And especially it involves a lot of arcsine, arccosinus things if one wants to do that directly, which is not really numerically stable if one does it. And so the idea is to obtain the isometric deformations of the third kind by mapping the T-hedra of the third kind to T-hedra of the second kind, transform them, and then map back accordingly. I will explain now how this is done. Now look here on the left, a picture of a T-hedra of the third kind. We consider the planes that contain the vertical lines. Then we can then we can shrink the edge length of the prism curve here in red to 0 so that the curve just becomes a single point. And by doing so, all these planes are transported parallelly to this point because we don't change the angles of the polygon, we only shrink the length to 0. And then after all these planes intersect in this one point, we can construct a new surface such that the edges of the new surface and the old surface are always parallel. Of course, the edge lengths are changed during this process, but then, yeah, doing so, we obtain a new surface which is of type 2 for a given surface of type 3. Algebraically, that just means that if you consider the motion part, that you just forget about the translation and only perform the stretch rotation. This map is highly not injective, since if we change the length of the profile prism curve, but keep the dihedral angles, then we will always project to the same curve of same surface of type 2. But if we now look at one vertical stripe of these surfaces, just here on the left, we can see, yeah, that the angles are the same and that the horizontal edges are the same, but that just in the vertical edges, edges that they are scaled. And so if we prescribe the edge length of a trajectory curve, given here in purple, then we can reconstruct the prism by computing its edge length. If we if we have a T-hydron of the type 2, then we construct accordingly a T-hydron of the type 3 that has the same angles, and after we prescribed the edge length of the trajectory curve. And if we do so, then we obtain an inverse, and that can be used to compute the isometric deformation of T-hydra of the third kind by first projecting to this corresponding surface of type 2, deform it isometrically, and then project back to the third kind. And this process, this diagram commutes because all the corresponding edges of these two surfaces are always parallel, and hence all the angles are the same. And if we do so, we obtain here this following deformation, isometric deformation of the surface. And again, we can see that the profile curve get bended in this one direction, and the others just get more curved, and the other curves get less. All right, that is my part about the discrete T-surfaces, the T-hydra. And now I will stop sharing, and Arvin will continue with the smooth T-surfaces.
Hello, everyone. I'm Arvin Rasoulzadeh, and I take on the talk from here on from Jonas. Just there is a problem that I can't make it full screen. Apparently, when I make it full screen, it stops sharing a moment. I think it should be good. Okay. So, first of all, I would like to thank you for this opportunity for giving the talk here at the Fields Institute regarding our new research with Jonas. From now on, I will talk about the T-surfaces, which are the smooth counterparts of the T-hydra. And my plan is here to talk about their construction, and in addition, about their isometric deformations. And finally, I would like to show you some animations regarding these deformations. So As Jonas mentioned, in a close analogy to the discrete differential geometry, the discrete T-hedra, these surfaces are characterized by the profile curve, the prism curve, and the trajectory curve. So if we somehow assume that we have a refinement of these curves, like if we have the smooth versions of them, as you can see on the picture on the top right, for the profile curve in blue, for the trajectory curve in purple, and for the prism curve in red, then we obtain what that we call a T surface, which is a smooth version of the quad surfaces that Jonas was talking about. So exactly like the classifications that Jonas did, we would like to continue with the classification in the smooth version. Regarding the T surfaces of the first kind and the second kind, this is something straightforward. If we in fact have a planar smooth curve like delta, the smooth version of the delta that Jonas introduced, then we can have the smooth motion path of the first kind, where it is related to this delta via this translation matrix that again Jonas mentioned on his slides. And regarding the second kind, we will have the scaling and rotation matrix, as you can see on the bottom part of the slides. However, in the case of the smooth motion paths of the third kind, the situation is a bit more complex, and we give it as a lemma, as you can see, where this rotation matrix appears on the bottom left. So in this way, we assume that theta would be a smooth function and a strong monotone function. And having this rotation matrix, actually, we can build up the smooth prism accordingly in such a by assuming that the unit tangent to the prism would be like the first column of the rotation matrix. In such a way, we would have the tangents to the prism, and from there, solving this differential equation would allow us to build up the prism. Here, I would also like to give you a matrix representation of the smooth motion path of the third kind, as you can see on the top. And our T surfaces, in an exact analogy to the T-hedra, are obtained by the action of our smooth motion paths on our smooth profile curve this time. So we will call them in exactly the same way, T surfaces of type 1, 2, and 3, where I have given you the parametrization of these T surfaces below. The classification is also follows closely to what Jonas said. I just go through it in this smooth version. Just instead of rotation matrix, I just have put the row dot there because we know that they are closely related now. Yes, regarding the smooth translational surface, we can see that we only have the scaling factor is just 1, and we only have a trajectory which plays the role of the translation. Regarding the surface of revolution, we see that we only have the rotation, and if we add the scaling, then we obtain the T surfaces of type 2. And regarding the molding surface, we have the translation and the rotation part. And if we add the scaling, which if we have scaling, rotation, and translation, which is the most general case for us, we obtain the T surface of type 3. Well, having the classification of these smooth motion paths on our Lie group and having access to these parametrizations, we would like to take another step and obtain the isometric deformation of these T surfaces. But we are not just looking for any isometric deformation. Exactly like what Jonas said, we are looking for the class preserving isometric deformations. Again, where this TK in the formulation that you see is the classes that Jonas just introduced. With difference that now we have a continuous map from this open interval around 1 to our class in such a way that our first fundamental form now should be preserved. And at the time beta equal to 1, we would have our normal parametrizations that are just introduced. Just for a very short remark, I would like to mention that this preservation of the first fundamental form is actually playing the role of preserving the quad in the discrete case. In fact, our first fundamental form is in the form of a 2 times 2 matrix with the components E, F, and G, where E and G contain the our tangent vectors to the two coordinate curves, while the angle between these two tangents is encoded into the part F. So that's how you can see it's related to the quads that Jonas was somehow mentioning. So what we want to do in order to find the isometries is that we must find now parametrizations of our surface that are time dependent. By time, I mean dependent on beta. So this is, and we know that it should preserve the first fundamental form. So this would be equal to solving a system of differential equations, where I would like to write them like this, with E equal to E tilde, G equal to G tilde, and F equal to F tilde, where the tilde versions of everything that you see here means their time dependency. For all the, so our strategy for solving this system of differential equation would be as follows. Well, the part E equal to E tilde is a differential equation that contains information on the deformation of the scaling factor and our profile curve, and is identical for all the T surfaces. So solving this differential equation results in knowing how our scaling factor would change and how our profile curve would deform, which I have given you the formulas in the boxed version here, which if you even compare with Jonas formulas, you would see that they have a close resemblance. The rest of the differential equations allows us to obtain the deformed version of the prism. So they would let us know how the prism gets deformed. So now having access to the parametrizations and knowing how these surfaces deform, I can show you some animations then. So for the case of T surfaces of type 1, the translational surface, I would like to mention again that they are obtained by moving a profile curve along a trajectory curve. So their final formula for them would be as follows, as you can see in here, that the red part is just about the deformed z coordinate of the profile curve, and the second part, the second entry actually is just obtained from the arc length parametrization of the trajectory curve, and the first part shows how the trajectory curve, at the same time, profile curve, one of them is squeezed and the other one is stretched, and this results in these animations. So that I would like to share with you. You can see that they're somehow, I don't know how to say, somehow squeezed, these surfaces. And this process happens in an isometric way. T surfaces of type 2. Well, these, as we mentioned before, these kind of T surfaces are obtained by the action of the smooth motion path of the second kind on its action on the profile curve. I get here on the bottom, I'll give you two pictures of these kind of surfaces from a top view with two different scaling factors, and their parametrization is given here. So their time dependency isometric deformation, the formula for it is given here, where you can see that the red part is exactly identical like the previous case, and the first entry is different from the parametrization that I give you here, just by rho being replaced by rho tilde and mu being replaced by this square root, which refer to the change of the which refer to the deformation of the scaling factor and the prism itself. I would like to share some animations with you regarding two kind of T surfaces that are built. While the one on the left has a circular profile curve and the other one on the right has a parabola one. And you can see how they deform exactly like the case that Jonas mentioned. The profile curve is getting less curvy while the trajectory curve is getting curvier. I would like to also mention a special special class of the type 2 surfaces. These are the surfaces of revolution, which if we solve the equations for theta tilde, you can see that complex equation will just turn into this simple one. And I would also like to mention that these surfaces are first time investigated by Minding in 1838. This class of surfaces, the trajectory curve and the profile curve, play the role of the principal curvature lines. And as we know by the famous Gauss theorem, since the isometries should preserve the curvature, these curvature lines, one of them should lose curviness while the other one is gaining curviness. As you can see, the profile curve is getting closer to a line, while the trajectory curve is getting curvier and curvier. The final class of the T-surfaces, and actually the most complex one, is the T-surfaces of type 3, which are obtained by the action of the smooth motion path of the third kind on the profile curve. Again, I put some pictures for you with different scaling factors to see how this surface looks from the top side. Solving the isometric deformations of these T-surfaces actually can be quite complex, but fortunately we have this theorem, which the core of the theorem is this, that says that if we have solved the isometric deformations of the prism of the T-surfaces of type 2, we already have most of the materials to know the isometric deformation of T-surfaces of type 3, with the exception of V-tilt, which V-tilt itself can be is referring to a change of parameters, which itself can be solved from the differential equation F equal to F tilt. So finally, if I want to give the formula to you, it's again, like always, the last row refers to the deformation of the Z coordinate of the profile curve. And the first entry would be only different from the T surfaces of type 2 due to the fact that rho tilt and V tilt appear there as well, which is natural since we are now moving along the prism. One of the special classes of these kind of T surfaces, which also appear in industry a lot, is called the molding surfaces. So that's why I give them another slide for them. If we simplify the equations for theta tilt and V tilt, we see that those complex equations will just fall into simple case where it's boxed here. And theta tilt will then be nothing but the total curvature of the prism divided by beta, which tells us that as this beta goes up and down, we are expecting to have a prism that is getting either curvier or getting closer to a line, which I can show you in this final videos. These are two cases of the molding surfaces where the profile curve and the trajectory curve are again the curvature lines. You can see again, due to the fact that the isometric deformations should preserve the curvature, you can see that the curvature of the principal curvatures, one of them is decreasing while for the other one is increasing. So the profile curve is getting closer to a line as they twist back around the z-axis, while the other one gets curvy. So finally, I would like to thank you for your attention, and so maybe we move to the question parts. So depending on where the questions belong, Jonas and I would answer.
Great. Thank you, Jonas. Thank you, Arvin. Those were really interesting topics. Yeah, so as I said, is there any questions? Oh, there's a question in the chat asking what software you're running for the animations.
Please, Jonas.
Yeah, I was using Houdini, which is a software that is normally used to produce, I guess, to produce video games or just comic movies. But they have also implemented something like a half-edge data structure and quaternions, which makes them very useful to do visualized mathematics into discrete. And for the smooth animations, Arvin was just using Maple.
Yes, I was using Maple because I mainly wanted to produce the animations exactly based on the formulas that we had found for the smooth part. I mean, of course, in the case that whenever you want to create animations or things of this kind, you can always rely on discrete case by increasing the number of breakpoints. But since Jonas and I wanted to have it in a separate way, Jonas produced the discrete animations with Houdini, and I produced the smooth animations, which are the result of direct computation of integrals with Maple.